In the next two lessons, we're going to look at displacement reactions in the context of the reactivity series. And in this lesson, we're going to look at the thermite reaction. Now, a displacement reaction is a reaction in which a more reactive metal displaces a less reactive metal from its compound. And in this case, in the thermite case, we're looking at from its oxide. And as you'll see in a minute, it's a thermite reaction because it involves the release of a lot of heat. So let's take as an example the reaction between aluminium, here in this baking tray, and iron oxide. This is actually iron 3 oxide. This is commonly known as rust. Okay, and you see that iron is here in the table and aluminium is here. Okay, so we mix these together. So here you have the mixture of aluminium and iron oxide. Now you can watch this video in the practical demos section of the website. And in the middle of this mixture I positioned some magnesium ribbon, which I'm going to use as a fuse, and I've added a bit of sodium nitrate, which is going to be used as an oxidizer. We'll explain why we do this in a minute. And well, you can see the reaction taking place here, so you can see quite clearly there's an enormous amount of heat released in this reaction. So let's look at this displacement reaction. So we can see that what happens is the aluminium, which is a more reactive metal than iron, kicks the iron out of the iron oxide and forms aluminium oxide, which is a more stable compound, and releases iron. Now there's so much heat produced in this reaction that the iron at this stage is in the molten state, so it's quite an impressive reaction. Now this reaction can only take place if the metal that is doing the displacing is higher up in the reactivity series than the metal that is displaced from its oxide. So aluminium will displace iron from iron oxide, but iron, for example, cannot displace aluminium from aluminium oxide because aluminium is higher up than iron. Let's just write out the symbol equation for this. So we've got aluminium plus iron oxide, and as I said earlier, it's iron 3 oxide, so the formula for that is Fe2O3 gives us Al2O3, so that's nicely balanced. What is interesting to do here is to have a look at what is called the energy level diagram for this reaction. So we've got the reactants here, which are aluminium plus Fe2O3, and the products, aluminium oxide plus iron. And you'll notice that the reactants are higher up in the energy level diagram than the products. That means that this is what we call an exothermic reaction, which means heat is released during the reaction, and the heat that is released during the reaction is represented by the difference between these two energy levels. Okay, so we're dropping from a higher level to a lower level. Now we call this heat delta H, which is also known as the enthalpy of the reaction. And when the heat is released, the enthalpy is negative. So we'll say that's negative. And obviously, as you can see in this reaction, the enthalpy is also very, very large indeed. There's so much heat released that the iron is initially in its molten state. Now, you'll also notice that in any type of reaction like this, there's a kind of hill here. All right, so in order for the reaction to take place, we've got to get over this hill. Now, the energy required to do that is called the activation energy. This is effectively the energy required to break the bonds in order for the reaction to take place. Okay, let's write that. That's activation energy. Now, in this particular case, it's the energy required to break the bonds of iron oxide. Now, that's not going to happen just by mixing the two in a flower pot. We've got to literally kickstart that reaction, and so this is where the magnesium ribbon comes in. Okay, we've got the magnesium ribbon, and that mixed in with the oxidizing agent So when the magnesium ribbon burns, it gets very, very hot indeed. It releases a lot of energy, and that combined with the oxidizing agent, that helps to introduce more heat into this reaction to kickstart the reaction between the aluminium and the iron oxide. So these are used really to get the reaction going. But once the reaction is going, then there's enough heat, there's enough enthalpy here, heat released from the actual reaction itself, just to keep the thing going. So we only really need this to get over the initial activation energy. Now, just to finish off, we can also predict how various thermite reactions might go by looking at the relative positions of the metals and the metals in the oxides on the reactivity series. For example, we would expect that if we mixed aluminium powder here with copper oxide rather than iron oxide, then we would get a much more energetic and violent reaction, which is in fact the case, and you can watch this on the video. So, and the reason for that is because the difference between aluminium and copper there in the copper oxide is much greater than the difference between aluminium and iron in its oxide. In the next lesson, we're going to look at a different type of displacement reaction in which a more reactive metal displaces a less reactive metal from the solution of its salt.